could be used in the future. Therefore, we examined the individual process steps of remanufacturing and examined the possibilities for using AI in each of them, beginning at the reverse supply chain and ending with the assembly steps. So in the reverse supply chain, we are confronted with problems such as unknown quantity, quality, and variety of products. So we need to determine if the product can be used for a direct reuse, repair, for remanufacturing, recycling, or disposal. So on one hand, this leads to a problem when we need to plan the transport of the product, and on the other hand, it also leads to a decision problem as to which procedure is the most suitable. In our literature research, we have found out that the existing research on using AI in the reverse supply chain mostly concentrate on the general network design to establish an infrastructure to manage the reverse channel. So the mostly used methods for the network design we found are genetic algorithms, taboo search, or fuzzy systems. In the intralogistics for remanufacturing is different from the new part production because of the uncertain conditions of supply and supply of the product. So error conditions may occur, therefore rescheduling in the actual procedure is necessary. We found different approaches for the optimization of transport routes and machine utilization. In most of the research, we found the planning of the transport routes and the processing are viewed separately. For example, this can be achieved through the use of meta-heuristics or hidden Markov models. Another approach we found there the planning of the process steps and the transport routes are viewed simultaneously with the help of a constrained programming, so a good result can be achieved. Thereby, it can happen that finding a solution takes a very long time. However, this can also be aborted and the best solution up to that point can be applied. The products that are to be remanufactured have different conditions because of the diverse ages and the different stress and strains arising by the user. Furthermore, the remanufacturing companies aren't involved in the history of the product. So the test procedure has to be managed for the varying conditions. The functional test of the products is of greater importance for mechatronical components. So to make the test more efficient, an automatic testing is necessary, but it has to be first developed for each product, which can almost only be provided by large companies or the original equipment manufacturers themselves. In our research, the possible test methods we found can be divided in the following categories. For example, the signal-based methods, which are absolute value control or trend control, signal model-based methods like in spectral analysis or random calculations, and model-based methods, for example, artificial neural networks, fuzzy methods, or parameter estimation. So now we come to the disassembly step. It is an essential process step in remanufacturing, and it needs to be as low destructive as possible to keep the original design of the product. But we need to sort out the wear parts. So for an automation of the step, a knowledge base about the product is needed. For example, this knowledge base can be generated via reverse engineering or from the data the OEMs can provide. But a full automation is difficult due to the variety of variants, wear, corrosion, or contamination. So a possible solution is a flexible automation through human-robot collaboration. Through the use of object recognition and semantic analysis, human-robot collaboration can be made more efficient. Another important point in the disassembly is the planning of the actual disassembly. In our research, we found that for the disassembly sequence planning, meta-heuristics methods like genetic or evolution algorithm are mostly used. Now we come to the cleaning part. At present, this process step is usually fully automatic and independent of the actual degree of soiling of individual old products. In the context of cost optimization, This process step could also be performed by robots adapted to the contamination pattern with optimization of the robot path and visual pattern recognition for localization of the contamination. Different cleaning methods are conceivable here depending on the type and location of the contamination. However, in our research, we didn't find an approach for this example. The inspection. At the moment, the inspection of the individual parts is mostly carried out by suitable, qualified and experienced workers via a manual visual inspection. The inspection in particular can benefit from advances in the field of machine vision. With these image processing systems, many individual parts can be inspected visually and also measured very quickly. Especially methods for pattern recognition or artificial neural networks are receiving more and more attention. ANNs have the advantage that they can also be adapted to different product variants, which is often difficult with other methods. The refurbishment. This process step is concerned with the restoring of the dismantled and cleaned individual parts to a new condition. This can be done, for example, by additive manufacturing processes such as build-up welding or 3D printing, or the production to the next nominal dimension, or if you need to apply a new coating. The reconditioning methods depend on the old part or the respective components and are already defined at the process design stage. So far, refurbishment has not yet benefited much from developments in artificial intelligence. The existing solutions are usually based on the fact that after cleaning, all parts are in a similar condition before reconditioning. For example, before a coating process, the old layers are completely removed, even if only a part of the coating is damaged. So the individual differences in wear and tear are no longer present later, and the old parts can be treated in the same way, often fully automatically. Other parts with larger traces of wear are often refurbished manually. A possible way for a specific refurbishment is to compare the known product data with the actual condition after inspection, so you can do a part-specific refurbishment. So now we come to our last step, the assembly step. In terms of complexity, assembly is a similar process to disassembly, but it's easier to solve. You can, for example, invert the disassembly order to an assembly plan for the particular part. So the same approaches and procedures can be used with the special feature that the starting position and orientation, as well as the condition of all individual parts are known. Here, the human-robot collaboration is also a possible way to create a flexible automation for the increasing variety of variants. So now we come to the conclusion of our research. When looking at the sub-processes within remanufacturing that have been realized with AI to date, it is noticeable that these are mainly processes that are also found in a similar way in new part production. For example, the intralogistics, inspection, and the reverse supply chain. Other processes, such as cleaning or refurbishment, are much less represented in the research context, but also consist of a combination of several disciplines like pattern recognition and intelligent path planning. The integration of AI has not been solved completely in any of the sub-processes. Even for the processes that relatively often represented, there is still much potential for further research. One reason for this is the fact that most AI methods are data-driven, and the majority of remanufacturers are small independent companies that can hardly generate such data on their own. So the original equipment manufacturers could use these data-driven AI methods, but they often do not remanufacture themselves. So, thank you for your attention. If you have any question, you can ask them now.
Thank you, Lars.